This is section 15.6, number 7, and this one's our first spherical triple integral. So we're going to evaluate this one by spherical coordinates because of this condition right here. We want to remain inside of a sphere of radius 2 centered at the origin, and so that condition there makes spherical coordinates most preferable. Okay, so to do the conversion, let's recall that x is equal to rho cosine theta sine phi, and y is equal to rho sine theta sine phi. And if we had to substitute for a z, which we don't have to here, it's rho sine phi. Okay, so using those, we can see that this integrand here is x squared plus y squared, so that's going to be rho squared cosine squared theta sine squared phi plus rho squared sine squared theta and sine squared phi. We can factor out a rho squared, sine squared phi from each. What's left is cosine squared plus sine squared, which is 1. So the integrand is rho squared sine squared phi. Now, in addition, we'll be multiplying that by something when you want to calculate the differentials for integrating a dv in spherical coordinates. It's not just d rho, d phi, d theta. Remember in cylindrical coordinates we had to use the r d theta? Well, this time that r for d theta is actually the projection of rho into the flat plane, and that's rho squared sine phi. So that represents the radius, and then you've got the 3 integrands, or the 3 differentials. So this is dv, that is, this isn't part of the integrand, this just comes along for the ride in spherical coordinates. So this will have to be multiplied by this in order to build our actual integrand. Okay, first our limits of integration. It's a full sphere with radius 2, so rho is going to go from 0 to 2. Theta goes the full circle, 0 to 2 pi, because it's the angle in the flat xy plane that defines the sphere. And then finally phi itself starts at 0, pointing straight up along the z-axis, and it increases as you swing it around to the negative z-axis. So it runs from 0 to pi. And notice, no functions in this, so we can do them in any order. So I'll go phi first, 0 to pi, and then theta next, 0 to 2 pi, and then we'll do rho first, so 0 to 2. Again, the function's going to be the integrand plus the differential piece, so it's going to be rho to the 4th, sine cubed phi, and then the order we have it here is d rho, and then the next one out is d theta, and finally d phi. And if we go ahead and evaluate this, we get the very obnoxious 256 pi over 15. And that's it. So that's our first spherical integral. And again, one of the main reasons why you would move it into different coordinate systems, it simply makes it easier. These would be rather unpleasant limits if we left them in rectangular coordinates for the sphere, and the limits turn out to be much easier to plug in. Even the integrand turns out to be easier.